Hi everybody, Dr. Pingle here. We're going to cover a little bit on focal statistics. So focal statistics is a really handy tool in the ARC Pro toolbox. And what it does is it lets you make calculations on a sliding neighborhood. So essentially what you can do is define a neighborhood, say of 3 by 3 pixels, or the 8 pixels surrounding a central pixel, and say what's the average pixel in this group, or what's the standard deviation of the pixels in this group. You can find the maximum, you can find the minimum. There are a lot of applications, and so to demonstrate this, we're going to work with some elevation data. So this is a DEM that I downloaded, just a random section of SRTM, so just a little bit east of St. Louis, between St. Louis and Lexington, Kentucky. The very first thing that we should always do if we're working with elevation data is reproject it into a local coordinate system. So we are going to do that. So we're going to use the project raster tool and project this into UTM coordinates. So our input raster is going to be the one we've got loaded over here. We're going to project this. Right now I've got this set to project into my geodatabase here, which is fine. And then we need to figure out where this is going. So lots of ways to do this, but I find that this is the fastest for me. You can pull up a larger one if you want. Here we go. So we are going to be somewhere, I think, in zone 17. So we're just a little bit under. What is that? Lake Erie. We can zoom out to confirm that. Oh, actually, we're probably one over from that. We're under Lake Michigan here, so that's likely to be zone 16. Okay, so we're going to project this into UTM 16. Remember that nearest the resampling technique is a very, very important bit here. So you can choose either cubic convolution or bilinear interpolation, but definitely don't choose nearest neighbor unless you've got a very good reason for doing that. We'll go ahead and run this, and I'll pause the video while it processes. Okay, we've got a better rendering here, and I'm just going to make sure that we choose a symbology that's going to look a little bit better here. We can, let's see here, we'll show these names, and we'll just pick elevation 2 for now. We could choose something a little bit more pleasing to the eye if we wanted to, but this is probably good enough for now. Okay, so the next thing that I want to do is sort of just demonstrate a little bit what we're looking at. So we're just going to run a quick hill shade on this, setting this to our projected data, our output. This is totally fine, and we'll just hit OK. This should execute pretty quickly, so I don't think we'll bother pausing the video. Ready in just a second. Okay, so if we zoom in on one of these sections here, we'll get a good look at this. Now, what we want to do is use focal statistics to take a look at this data set. So focal statistics is in your toolbox. Basically, what we want to do is we're going to take an input raster. So we don't want to use our hill shade. We want to use our projected raster. We'll just use the default here for now. Now, what we're going to be doing is analyzing the neighborhood around a point. So if we zoom in far enough and we make sure that our appearance of our raster is actually set to resampling set is set to nearest neighbor, what that's going to let us do is let us see the real pixels in here. Now, I want to do this for a reason. If we're defining a neighborhood, what we can do is we can say, I want to define a rectangular neighborhood with a width of 3 pixels and a height of 3 pixels. By default, our unit type is going to be cell, but we could actually do this in map units if we wanted to. We could say a width of 1 mile or half a mile, whatever our units are here. So you have to keep in mind that this is in meters. And so by default, if we put in 3 and 3, that's going to be 3 meters and 3 meters. Most people are pretty willing to run focal statistics with a pixel-based neighborhood rather than a map-based neighborhood, but you may you can decide that based on the problem that you're working on. So in this case, this is going to be a 3 by 3 neighborhood. So let's pretend that we're calculating around this central pixel. We'd look at this one, this one, this one, these 3, and these 3 in this square of 9 pixels with this one at the center. Now we can calculate a lot of different kinds of statistics. We can calculate means, we can calculate maximums, minimums, the range, the standard deviation, the sum. And essentially what we can do then is we're moving this sliding neighborhood or the sliding window around. And for every central pixel, we would calculate this according to the neighborhood. So let's take a look and just do this by example. We're going to set a width of, oftentimes it's actually better to set this at an odd number because you're including the central pixels. So we'll set this to 11, 5 pixels to the left, 5 to the right, and then the center one, and then 5 pixels up and down. And we're just going to calculate the mean for now. And I'm going to make this the mean so that we know what it is. Okay, so that's been calculated. I'm going to zoom out for just a second so you can see what we've done. Now I'm going to uncheck these two. So at the very top, we've got our focal statistics. At our bottom, we've got our original raster. We'll get rid of our unprojected raster. And what I want to do is look at the appearance here and change this symbology to the same thing that we had before. There we go. Now, what I kind of want to do here is set these to the maximum and minimum for now. And in fact, I can we could define this as custom and change these around. I want to do that just so that I can make a very direct comparison. So I'm going to set this to 50 and we'll say 725. And then we'll do the same thing with this one. So we're going to set this to minimum and maximum with a custom statistics. Nope, we're not allowed to change that. Okay, so we're going to change the other one to negative 47 and 770. Negative 47, 770. Okay, so the point of that is just to make sure that these two are the same. So now this one goes from negative 47 to 70. This isn't updating. This is unfortunately just a bug. But what we should be able to do now is take a look at these two directly. So as we slide this window, what we're doing is we're peeking underneath here. So look very closely at this area right over here. What you can see is that as I move downwards and we're looking at the original data, that's a lot more detailed than this one. If we zoom in, we can actually set this to DRA, which is dynamic, which is going to enhance the contrast. We'll do that for this one as well. So essentially we're calculating this window, we're calculating these statistics for only the window that we're looking at. That's going to lead to a slight mismatch on the color, but that's okay. All right, so we're moving down. So notice all the detail up here. This is our focal statistics at the top, and as I swipe down, these are the original data. So what you can see is that we've aggregated, right? We've smoothed this. If we're doing a mean filter, we're taking a neighborhood and we're saying for each central pixel, calculate the average in that sliding window. So that's why everything starts to smooth out a little bit. A mean focal statistics will tend to smooth the data. Now, why might you want to smooth the data? You might do that for several reasons. One would be to generalize the feature. So to illustrate this, we're going to calculate contours. So we're going to take our input raster as our projected data. So this is, we're just going to call this contour original. We'll make our contour interval, just to keep things simple, I'm going to make it 20, we'll make it 20, which is a little bit large. Everything else is going to stay the same. So we'll run that. This might take just a second to run, so I'm going to pause the video. Okay, so those contours have run, and I'm just going to zoom in here so that you can see them. All right, so this is an example of what our 10-meter contours look like. So these were calculated on our original data, so you can see these contours lining up with our original data quite well. And as we kind of pan around, actually, let's zoom up into the mountains just a little bit here. Turn the hill shades back on. Okay, so you can sort of spot this riverbed in the terrain. And then these are the contour intervals corresponding to all of the little twists and turns of the terrain. Now, so you can see them kind of matching up to the riverbeds, for instance, pretty nicely. We're going to run this again, only instead of having our input raster here, we're going to use our focal statistics as our input. The output feature class, we're going to call this contour focal, but we're going to have the same contour interval as we did before, 20 with a base of 1. So we're calculating these contours just like we did before, except we're calculating it on this mean surface, the surface that has been smoothed using the focal statistics tool. All right, so in blue, we have these smoothed contours. In white, we have these aggregated, or we have these original contours. So let me uncheck some of this stuff so you can kind of see what's going on. Essentially what we've done is this is a generalization technique, right? So we're trying to show the overall shape of the landscape without getting into too many of the details. So we looked at generalization as a technique. So we could generalize polyline features. But what would have happened if we had tried to run a smooth line on these features? We wouldn't have gotten this sort of nice surface that we had generated before. Yes, we could have simplified some of these shapes, but what we would have been left with is something much more complex and maybe difficult for people to understand. So by pre-smoothing our DEM, we accomplished the same thing, but with much nicer, neater contours. Okay, so let's talk about one other application of focal statistics. So we're going to run this one more time. So our input raster is going to be our original data again. Our output raster, we're going to call focal statistics, but we're going to call it standard deviation. We're going to do another rectangular window. You can experiment with these if you want. Just so you know, there are all kinds of different shapes. You can actually have what amount to three-dimensional shapes by giving different weights. But most of the common ones are going to be either a rectangle or a circle. Instead of the mean statistic, which would act as a smoother, we're going to use standard deviation. So standard deviation is a way to quantify the variability in a data set. So how much do the numbers deviate from the mean? We're going to go ahead and run this. What this is going to have the effect of doing is quantifying, or it's one measure of quantifying roughness. So what we're doing is we're saying how much variability is in the surface. Is it craggy? Is it flat? And so this is one way of doing that. I'm going to uncheck those contours and zoom out a little bit here. What you're seeing here are lines that in some ways amount to slopes. So if we ran a correlation between these, we would find that there is a correlation between slope and standard deviation within the neighborhood. But essentially what we're saying is we're trying to calculate roughness. Now what we should find is that, and we could probably change this so that instead of white being rough, black is rough. So let's go ahead and do that. So we're just going to change the symbology. and reverse this. Okay. What we should see when we do that is essentially that features that we think of as flat or planes are going to show up with a very low roughness, right? So this riverbed, for instance, is showing up with very low roughness. But some of the areas around are going to show up as more as rougher, right? So this is an area where the terrain is rougher from this perspective. There's an area where the terrain is rougher. There are much more advanced ways of quantifying surface roughness. Here we can see an area that is quite rough. So there are many ways of quantifying roughness, but standard deviation using focal statistics is one kind of simple way that you can get at that idea. So there's a quick introduction to focal statistics. It's an astoundingly powerful tool. I would encourage you to practice, set different neighborhood sizes, set different neighborhood shapes, calculate means, medians, standard deviations, ranges, and see if you can kind of predict what it is that you're measuring. Again, this is a very powerful tool, and learning how it works will benefit you quite a bit down the road as you're doing spatial analysis and data processing. Thanks for listening. Bye.